So, first thing, there is a typo. Oh, no, I did fix it on yours, did I? I redrew it? Okay. It says 3 toothpicks are used to form a triangle. There's the first one right there. 3 toothpicks, use your imagination. And then I formed a second triangle by adding 2 toothpicks to the top right corner, like that. Part A says, draw the next 3 diagrams in the pattern. I'm going to continue. So here's my original 3 toothpicks. Write this down. I added 2 toothpicks to get a brand new triangle. I'm going to add 2 more toothpicks. It's going to look like this, Curtis. Dunk. Dunk. That would be the next diagram in this pattern. What would the next diagram in this pattern look like? Well, it's going to be the original one, which is boom, boom, boom. And then I would add, there's something to write with? Writing this down? Okay. Then I would add 2 more toothpicks. Yes? Spot in the pattern? Let's do one more real quick. It would be the original, add 2, add 2, add 2, and we would add 2 more. So it said draw the next 3 diagrams of the pattern. I think the next 3 diagrams would look like that. And I could keep going and go, but I spotted the pattern. What we want to do is we want to try and turn this picture into a table of values, into an equation, into a graph. Follow that? So we're going to relate the number of toothpicks to the number of triangles. How many toothpicks in this first picture right here? 3. How many triangles? 1. How many toothpicks in this second picture here? How many triangles? So we could say that 5 toothpicks gives you 2 triangles. Or 2 triangles needs 5 toothpicks. In the third diagram, we have 3 triangles. How many toothpicks? Kira? 7. Spotted a pattern at all with the number of toothpicks? Oh, so you're saying this is going to be 9? You're saying this is going to be 11? I agree. Okay. And now we're going to graph this. On the y-axis, we're going to put number of toothpicks. On the x-axis, we're going to put number of triangles. And we can plot, we can make some points. The first point would be number of triangles 1, number of toothpicks 3. The first point on this would be 1 over 3 up, right there. Right? What would the second point be? 2 over 5 up. 3 over 7 up. How far did I go? 4 over 9, 5 over 11. 4 over 9 up. 5 over 11 up. Spot the pattern? Without bothering to get out toothpicks or draw a picture, if I have 6 triangles, how many toothpicks will I need? 13? Okay. What kind of a shape do those form? What kind of a pattern do you see? It's a straight line. Now, don't connect them. Here's why. Would it make sense, don't write this down, would it make sense for me to say that that was a point on this graph? Why wouldn't it make sense? How many triangles am I saying that is right there? 2.5. Can you have 2.5 triangles? You can have one triangle or two triangle or three. This is a fancy term. This is what's called a discrete graph or a discrete function. A discrete graph or a discrete function is a graph where you cannot connect the points because it doesn't make sense in real life. You'll notice last day we were used to using a lot generic equations, and so I was connecting the points like crazy because in the equation I can plug in anything. But for some real life situations I can't. Some I can. Some I can't. So it says, why does it not make sense to join the points together in a straight line? You can't have part of a triangle or part of a toothpick. Triangles and toothpicks come in whole numbers. There are lots of real-life situations that are discrete. Pizza toppings. Can you order one pizza topping? Yes. Can you order two? Yeah. Can you order three? Can you order 2.6 pizza toppings? No. They won't let you. Okay. I don't think they will. Oh, you can split a pizza in half, but I know you can split a pizza in half, but you're still paying for two toppings. I'm telling you right now. Okay? Try ordering 2.3 toppings. I guarantee the manager's going to tell you to take a hike. Or he's going to say, no, we'll give you 3 toppings and charge you for 3. The number of chairs in my classroom. Can I ever have 1.6 chairs? No. Number of students in my classroom. Can I ever have 2.8 students? Well, I got a kid who's really short. No, not unless something's gone horribly wrong, I'm telling you. Okay? But there are some functions that can take on every single value. For example, if I have a gallon bucket of water and I start to pour the water out, can I have 0.1 of a gallon that I pour out? Can I have 0.11 of a gallon that I pour out? If I measure really accurately, can I have 0.111123 of a gallon that I pour out? That would be an example of a continuous graph. Usually if you scratch your brain for a little bit, you can figure out whether, Marcus, you can connect the dots or not. E says, describe the relationship between the number of toothpicks and the number of triangles in words. Supposing I said we have 8 triangles. How many toothpicks? Can you figure out how to get there without having to build it? Or here's my question. Can you figure out some kind of mathematical trick that can turn a 1 into a 3, a 2 into a 5, a 3 into a 7, a 4 into a 9, a 5 into an 11? Sorry? Add 4? 3 it works. 2 doesn't work there. The dot. Yep. Ooh, what? For those of you that heard them, which is none of you, times 2 plus, is that what you said? Times 2? He said times 2 plus 1. Let's see. What's 1 times 2? Plus 1? Works. What's 4 times 2? Plus 1? Works. Remember I said how many toothpicks would 8 triangles need? I can tell you. What's 8 times 2? Plus 1? You need 17. F says, write it as an equation. Can do that. Y equals 2x plus 1. Yeah? Yeah. So now I can use this equation and I can figure out how many toothpicks if there are 36 triangles. Now, the number of toothpicks is on the y-axis, so 36 triangles, I think that's an x value. I think it's going to be this. Do you need a calculator? Maybe you can do this in your head. Yep. 73. And that's way faster than trying to build the silly thing. One of the things we try and do in math is spot a pattern, make a shortcut, and don't bother trying to do the rest of it yourself, right? 73. So if I tell you how many toothpicks, you can tell me how many triangles. I wonder if I can go backwards. If I tell you how many triangles, can you tell me how many toothpicks? Sorry, if I tell you how many toothpicks, can you tell me how many triangles? Let's see. It says, using the equation, determine the number of triangles if there are 83 toothpicks. Toothpicks, that was my y coordinate, right? You know what? I think it's going to look like this. 83 equals 2x plus 1. Yeah, we've turned the page now, boys and girls. How would I get the x by itself? Here's a bit of review of our equation solving from last year. Yep.
Move between the one toward the other side.
Yeah, how? Okay, when you're solving, because you're going back to where you started from, BEDMAS works in reverse. You do your addition subtraction first when you're solving. You do your multiplication division last when you're solving, which actually makes sense because you're going backwards to find where you started from. So I'm going to minus 1 from both sides. I'll get 82 equals 2x. And then, why divide by 2? We're also doing the opposite, fancy word, the inverse operation. So whatever you're doing to the x or to the variable, we do the opposite, the inverse. So it's going to be divide by 2, divide by 2. And by the way, I think it was Darian, you said divide by 2 minus 1. Actually, I think it's minus 1 divide by 2, which is why I didn't acknowledge you with your guess earlier. What do you get? And I don't need to build it to convince myself. Nice. Example 4. The table below shows the results from Mr. Dewick's physics class when they determined the resistance in an electrical current, an electrical circuit, by measuring the voltage, V, when the current, I, was passed through the circuit. So there's my table of values. Graph the following on the grid below. Label the axes first. Which of these is going to go on the y-axis, do you think? Voltage or current? And how can you figure out? Why current? Numbers are smaller, so you think those should go on the y-axis? Huh? Why voltage? I'm looking, there's a 48, this goes up to 60. I think they want me to put voltage on the y-axis here. Voltage is going to be the dependent variable. Current is going to be the independent variable. By the way, in physics, the abbreviation for voltage is a capital V. The abbreviation for current is a capital I. Why isn't it a capital C? 2 reasons. The letter C is taken. It's used specifically for the speed of light, which is very, very important to physics. Secondly, not all math was done by people who spoke English. Not all physics was done by people who spoke English. It's from Latin or French. I can't remember which. All right, let's plot these. Apparently when the current was, can I get it all on there? I'm going to have to shrink down a tiny bit. Sorry, folks. There, now I can get it all on one page. When the current was 0.5, the voltage was 6. 0.5, the voltage. Where would 6 be? How would I graph 6 here? How high is this right here? How high is this right here? So between 5 and 10 and way closer to the 5, yes? You eyeball it. And that's the limitation of graphing, is you got to sometimes eyeball things. About there. When the voltage is 1.5, right here. Sorry, when the current is 1.5, the voltage is 18, which would be just below the 20, about there-ish, yeah? When the current was 3 amps, the voltage was 36, which would be about there. When the current was 3.5, the voltage was 42, which would be about there. When the current was 4 amps, the voltage was 48, which would be about there. Okay, we've graphed it. Should we connect them? I don't know. We'll have to think about it for a second. Should we join these points together? Well, can you have a current with decimals? I even notice in the data. In fact, I can't have a current of 3.4 amps if I have the equipment. I can have a current of 3.41 amps if I have the equipment. So I think on the x-axis, we could certainly justify joining them. What about on the y-axis? Can I have any voltage that I want to? I think so. I think voltage and current are not discrete. They're continuous. I think I could say, and I would pull out a ruler if I could. Ooh, I can. By the way, let's use our imagination. If we have no current, 0, what do you think the voltage is? 0. I think it's fair to assume this graph goes through 0, 0. Not every graph does, but I think this one does. So you can take out either a ruler, or you can freehand if you're neat, or you can use a straight edge like from your day planner or something like that. I'm going to cheat and use this. Now I got to move this around a little bit. That I want to go right on there. And I want to go through as many lines as I can. I think I can go through. That's pretty good. I think something like that. Yeah? I got one point a tiny bit below the line. I got one point a tiny bit, or a couple points a tiny bit above the line. I'm pretty close. There's mathematical ways to draw what's called a line of best fit, but here in Math 10, we're going to say eyeball it as best you can. So, with this graph, can we join these points together? What did we say? Yeah, since we can have decimal values for the voltage and for the current. C says, use the graph to determine the voltage for a current of 2.5 amps. Okay? 2.5 amps on my graph is right here. What would the voltage be? 30? All right, smarty peoples. See how good you are. D says, write an equation expressing V in terms of I. Can you come up with an equation that will turn a 0.5 into a 6, a 1.5 into an 18, a 3 into a 36, a 3.5 into a 42, a 4 into a 48? Yeah.
It'd be 12x equals y, or y equals 1x.
Or, even better, V equals 12. I can even use the physics, the science variables that they gave me, and that actually makes it easier for me to read my graph. Yes? I'll use X and Y if it's generic, or if they haven't given me variables, like in the last one. Also, in the last one, I had toothpicks and triangles. I would have used T for both of them, which would have been a little confusing. Yeah, 12. Use this equation to determine the voltage when the current is 6.3 amps. Okay, what would the voltage be if the current was 6.3 amps? You might need to do some math. Yeah, 12 times 6.3. Don't all rush for your calculators at once or anything. I'm ignoring Ben because he's clearly playing along with this game, but some of you are drooling. What'd you get? 12 times 6.3. I should be able to do this in my head. 12 times 6 is 72. 12 times 0.3 is 3.6. 75.6? Someone double check me.
Yep.
Yes? Brady, in answer to your question earlier, do I need a calculator? Depends on who you are, mister. I can do decimals in my head. 76 volts. 75.6 volts. So here is your new term for today: continuous and discrete variables. So in the class exercise 3, the variables I and V, current and voltage, are examples of continuous variables, since they can take on every value within a particular interval. Or another way to think about it for a continuous: you can have parts of the item, parts of the thing, parts of the item is the wrong word, parts of the whatever you're looking at. You can have 1.6 of whatever you're looking at, or 2.8 of whatever you're looking at. In example 2, the variables P for, I guess, toothpicks and T for triangles can only take on limited values. You can't have parts of it. Those are called discrete. Or the way I think about it, discrete, you must have whole number values. You can't have chunks. Students are discrete. Cars are discrete. Even money is discrete. You can have decimals, but what's the smallest value of money that you can go to? A penny. Can you get smaller than that? Sorry, money is discrete. The smallest chunk it comes in is pennies. You can't have, oh, Brody, I owe you 0.00064 cents. Doesn't work. Doesn't work. Example 5. Oh yeah, turn the page. It says determine whether each of the following is discrete or continuous. The time taken to complete a 100-meter sprint. Convince me. Oh, could you finish it? First of all, no one, Usain Bolt's not going to finish it in 5 seconds, Mr. Olympic boy there. Can you finish it in 9.7 seconds? Yeah. How about 9.71? How about 9.071? How about 9.0007? Okay, I think that's what would be a good abbreviation to use for continuous. C, capital C, sure. B, number of students who passed Math 11. Discrete. The cost to order pizzas. Convince me. I've heard both now. Convince me. You can buy 1 pizza or 2 pizzas or 3 pizzas or 4 pizzas, but you cannot order 5.8 pizzas. There's a limited number of prices that will show up. The prices themselves may be decimals, but I think there's going to be gaps in between them. Yes? I think it's discrete. Shoe size. That's discrete. They only come in halves. Yes? Foot size is continuous because all of you buy a shoe that's the closest to your foot size. But many of you, if you wear, for example, a size 10 shoe, there can be plenty of people that have different size 10 feet, slightly shorter, slightly longer. But yeah, shoe size itself is discrete. Score in a basketball game. Are you saying you can't have 28.3 points? No. The amount of water in a bucket. That's continuous. It can take on every single value. The number of stars in the Milky Way galaxy. Yeah, it's a big number, but I'm telling you right now, I know that the answer isn't something, 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 0.3 stars. Right? It's going to be stars come in chunks of 1. The altitude of an airplane from takeoff to landing. I think it takes on every single height between ground and cruising height, and then again it takes on every single height between cruising height and landing. So I think that would be continuous. Is that okay? What's your homework? We're going to go back to assignment 1. We're going to hope there's no typos. Certainly you can now try number 4. You know what? I think you can do all of these. Actually, let me look. Yep. So I'm going to erase the little circle, and I'm going to say you can do 4, 5, 6, 7, 8, 9. Then we're doing some graphing practice here. Now here, since we're just using X and Y, we're going to assume these are continuous unless they tell us different. So you can connect the dots and make a little shape. Oh, and I know that number 1 is going to be a line. How do I know just by glancing at it it's going to be a line? If it was a curve, what would it have? Remember? It's a good trick. Weird stuff, exponents. In fact, you know what? 5 is going to be a curve. I'll tell you that right now. Okay? There's your homework. Holy smokes, you got all of class to finish that. You should be able to get it done okay in class.